Hello, for this video I'm going to talk about how we calculate the pH of a buffer solution. This is OCR A-Level Chemistry Specification 0.513. Right, when we're asked to find pH, we have to start by making sure we know what pH actually is, and it's negative log to the base 10 of the concentration of H plus aqueous ions. Now, this is governed by the equilibrium where our weak acid dissociates into H plus and the conjugate base. You should already be aware of the acid dissociation constant. So that's Ka, and it's essentially products over reactants, concentration of H plus multiplied by the concentration of the conjugate base divided by the concentration of the weak acid itself. Now, if we simply have a solution of a weak acid, we start off with a weak acid and it dissociates into equal amounts of H plus and the conjugate base, which means the concentration of H plus is equal to the concentration of the conjugate base, and so this becomes H plus squared, and if we rearrange it we can get the concentration of H plus using the equation square root of Ka multiplied by Ha. However, for buffers, the concentration of H plus is not equal to the concentration of A minus. For a buffer solution, you need lots of the weak acid, and then you need to add some extra of the conjugate base, so that you get lots of that, whereas there's only a little amount of this, not equal. So that means we're going to have to do a little bit of more work here. Again, we're going to have to be able to work out the acid dissociation constant, and it is going to come to exactly the same equation as we've used every single other time. It is always going to come to this equation, but because these two are not equal, we cannot say that there's an H plus squared. So we're just going to have to rearrange the whole equation to get H plus on its own. If you want to pause and try that yourself now, do so. I'll continue assuming you have paused. So we want to get H plus concentration on its own, so we're going to multiply both sides by the concentration of Ha, so we can say this, and then we're going to divide both sides by A minus, so that we get Ka times by the concentration of H plus divided by the concentration of A minus. Now I've separated these out because it's often useful for us just to be looking at the ratio of the weak acid to the conjugate base. And there are 4 possible examples or types of question that can be set. I'll try and talk through each of these. They're all going to use this equation here, which again is just a rearrangement of the one equation to rule them all. So, this is the one, I guess, that you really hope comes up in the exam. You are given the concentrations of both the Ha and A minus, and in this situation, the amount of weak acid is exactly the same as the amount of the conjugate base. Here's an example just to show you what I'm talking about. You're told that the concentration of ethanoic acid is 0.5 moles per decimeter cubed, and the concentration of ethanoate ions is also 0.5 moles per decimeter cubed. The Ka for ethanoic acid is 1.76 times 10 to the negative 5. So, here is the equation. 1.76 times 10 to the negative 5 times by 0.5 divided by 0.5. Well, 0.5 divided by 0.5 is 1. So, simply put, the numerical answer to this is 1.76 times 10 to the negative 5. So in this situation here, the concentration of H plus equals Ka. So hopefully you'll even remember that and won't need to go through the mathematical steps. If the concentrations of these two are equal, they cancel out. Concentration of H plus is the concentration of Ka, so to find the concentration, of H plus, you simply take the Ka and the pH, well, in this case, actually equals pKa. Annoyingly, this is the one time your examiner hasn't given you the pKa, but you're simply going to do negative log to the base 10 of 1.76 times 10 to the negative 5, and that equals, apologies, I've just misplaced my notes, 4.75. Okay, on to example number 2. Here, yet again, you are being given a concentration for HA, and you're being given a concentration for A minus. However, this time the concentrations are not equal. So the example question, concentration of ethanoic acid is 0.7, whereas the concentration of ethanoate is 0.5. We're going to use the same equation again. Right now, if you wish to pause and try this, please do so. So, assuming you paused, Ka, we're putting it in as given, and it's 0.7 divided by 0.5 times, my apologies there. So, we go through that, and the concentration of H plus equals 2.464 times 10 to the negative 5, and if we had to find the pH, then that's negative log to the base 10 of 2.464 times 10 to the negative 5, which equals 4.61. Now, it's worth considering here that you can use common sense approaches to check you've gone right. We have increased the amount of the weak acid compared to the amount of the conjugate base. So the very first example, we had 0.5 to 0.5. Now, we've put a little bit more of the weak acid in. This means that we are getting a slightly higher concentration of H+, which is leading to a lower concentration, a lower pH. So the higher concentration of H+, which leads to a lower pH. So again, if you've got more of the acid, you will therefore get more of the H+, and therefore the pH will be slightly lower. So again, we can just compare that. The next couple of examples I'm going to give, I've again used the same system, and we can see how changing these concentrations slightly is going to impact the pH and the concentration of H+. Okay. Example number 3 is where it gets just a little bit more tricksy. The good news is every individual step that you do is going to be a year 12 moles question, essentially. So here you are not directly given HA and or A minus. Sometimes they give one, sometimes they give the other. Here I'm giving you neither of them. So in the example, you've got 75 cubic centimetres of 0.25 moles per decimetre cubed ethanoic acid, and that is added to 50 cubic centimetres of 0.5 moles per decimetre cubed sodium ethanoate. If you're given this, if we think back to what we needed before, we needed the concentrations of each of the two chemicals. To get concentration, we need to know the number of moles divided by the volume. Well, hang on, I do have concentrations, but what I don't have is concentrations for the mixed solution, because you're adding two things together. So we're really going to have to go through a couple of steps. The first thing is work out the number of moles of each chemical that you are given initially, and then take that number of moles and divide it by the new volume. So, for ethanoic acid, concentration times volume from the values that we are given there gives us 0.01875 moles, and for the sodium ethanoate 0.025 moles. Now we can work out what the concentrations of this new mixed solution are. We'll take the two values we've just calculated there, and the new total volume is going to be 125 centimeters cubed, 50 plus 75. So I'm going to divide both of these by 0.125. What this gives is a concentration of 0.15 for the ethanoic acid and 0.20 for the ethanoate ions. So here we do have slightly more of the ethanoate than the ethanoic acid. So now we've got the concentrations. This is what we were given directly in the previous example. For this one we had to go through a process to get here. So we can take the exact same equation that we've had before with the same Ka, and this time it's going to be 0.15 divided by 0.20, and the value for that is 1.32 times 10 to the negative 5. So that's our concentration of H+. To find pH, we would take negative log 10 of that, and it equals 4.88. So the end step is the same as the previous two examples. Just a note on what these changing concentrations do. Here we have more ethanoic acid than ethanoate, so we end up with a pH of 4.61. When we swap and we've got more of the conjugate base, we end up with a higher pH because we have less H+ being involved. Okay, now we're going to go on to the final example, and this is a completely different way of making a buffer solution. The previous way of making the buffer solution would be that you take a beaker of ethanoic acid, you have another beaker of sodium ethanoate, and you put the two together. Buffer. There's a second way of doing this, and this is where you add a strong alkali to a weak acid. So here's my example, ethanoic acid, and we're going to add some sodium hydroxide to it. If you want to pause and see if you can complete the equation, that would be great. So hopefully what you realised is that you'll get a neutralisation reaction. We have sodium ethanoate, and we also get water. Why am I telling you this? Because look, here is our weak acid, and we can make the conjugate base from it. To have a buffer solution, we need both the weak acid and the conjugate base. We need it to be both ethanoic acid and sodium ethanoate. So this whole situation will only work if you have a lot of your weak acid and you add a smaller amount of sodium hydroxide to it. So, easy example, if I give you 1 mole of ethanoic acid, you need to add an amount of sodium hydroxide that is smaller. So let's say we add 0.4 moles of sodium hydroxide. The ethanoic acid's in excess. So up here what we should have said is add a strong alkali to an excess of weak acid. What we will have, 0.4 moles of sodium hydroxide will react with 0.4 moles of ethanoic acid. They're in a 1-to-1 ratio, and it will generate the equivalent number of moles of your weak conjugate base. So what we're going to have, it makes 0.4 moles of ethanoate, and it leaves 0.6 moles of ethanoic acid. At this point, we have the number of moles of each of the two chemicals, and what we could do is calculate the concentration, and lo and behold, everything will go as normal. If you wish to pause and re-watch this part, just to try and get your head around some complicated stuff, I would thoroughly recommend this. I would even recommend pausing before trying the example. So, in the example question that we've got here, 50 cubic centimetres of 0.4 moles per decimeter cubed sodium hydroxide is added to 100 cubic centimetres of 0.5 moles per decimeter cubed ethanoic acid. If you want to pause and try working your way through this and then reviewing it, I feel that would be helpful. Again, you can pause and try just stepwise. The first thing you will have to do is going to be just like last time, work out the number of moles of each. Then see if you can work out how many moles excess of your weak acid you've got, and work out how many moles of the conjugate base will be formed. Okay, let's work our way through this. So, let's go for the sodium hydroxide. 0.4 times by 0.5 is what we have to start. So that is 0.02 moles of sodium hydroxide. 0.5 times 0.1. I tried to keep the maths fairly easy this morning. That is how much ethanoic acid we have. This is in excess. All of the sodium hydroxide will react. So what will happen is that 0.02 moles of sodium ethanoate will be formed, and 0.03, that's 0.05 minus 0.02 moles of ethanoic acid will remain. So now we have the total number of moles of each. What we can do is work out the concentration for each. If you want to go and try and do that, and again check back in, hopefully that will help you. So here we've got the number of moles. We just need to go back to all the information we've been given. 50 and 100, the new total volume is 150. Remember to convert to decimeters cubed, so we're going to divide each of these by 0.15, and what we've got is these two concentrations: 0.20 moles per decimeter cubed of ethanoic acid, 0.13 recurring moles per decimeter cubed of ethanoate. At this point, we now have the concentrations. The Ka is the same as it has been for all of the other ones, so what we can do is work out the concentration of H plus. Please, in exam questions, write the whole things out. To save you time whilst I do this on the video, I have put HA, but we've got 1.76 times 10 to the negative 5 times by 0.2 divided by 0.13 recurring gives us 2.64 times 10 to the negative 5 moles per decimeter cubed, and the pH from that is going to be 4.58. There's quite a lot in this. It will be a rewatching. I do hope this has helped explain this topic.